Alright, so we're going to do one more curve sketching example for Math 1560, Calc 1 at U of L for fall 2017. So this time we're going to do an example involving a trig function, okay, sine 2x minus 2 sine x. And remember, you can't pull constants out of the trig function, so sine 2x is different from 2 sine x, so this isn't a function which is identically 0. Now, here we have one additional observation that we need to make, which we don't really use when we're dealing with other graphs. So the observation that we make is we note the following. F of x is what's called periodic. Okay. So what does it mean to say that the function is periodic? It means that f of x plus 2 pi is the same thing as f of x for any real number x. So the graph repeats every 2 pi, right? We know this because we know that the sine function is periodic with period 2 pi. Sine 2x is actually periodic with period pi, but the entire thing repeats every 2 pi. And what that means is that we only really need the graph on the interval from 0 to 2 pi. Once we have the graph from 0 to 2 pi, well, then we can just keep repeating it, so we can make copies. So for each interval, so from 2 pi to 4 pi, and from 4 pi to 6 pi, and from minus 2 pi to 0, and minus 4 pi to minus 2 pi, we can just put additional copies of the graph. Okay, so we have that observation which we need to make. Now, once we've made that observation, we can continue. What else do we notice about the function? We start with the function itself. We know that the domain is all of R. What about intercepts? So for intercepts, we have to be a little bit more careful. We need to find, so x-intercepts in particular, we want to know where this function is equal to 0. One of the ways to do that is to apply an identity. Okay, so notice, so sine 2x, there's a double angle formula that says sine 2x is 2 sine x cos x. Okay, and then we see that we have a common factor. 2 sine x shows up in each term. So if we factor that out, we get to there. F of x is 2 sine x times cos x minus 1. So f of x equals 0 when sine x equals 0, and that would mean that x is equal to, well, minus pi, 0, pi, 2 pi, and so on, or when cos x equals 1. But actually we already have that covered, right? Because when is cos x equal to 1? Cos x is equal to 1 when x is equal to 0, 2 pi, 4 pi. So those zeros are already accounted for. And so notice that f of 0 equals 0, so the y-intercept is also one of the x-intercepts. So we've got the intercepts. Domain is R, and since the domain is R, we know that there are no asymptotes. The only other thing we might want to do is can we do a sign diagram for f? So that's a little bit trickier. So if we want to do a sign diagram for f, and we're just going to do it between 0 and 2 pi, because remember the graph repeats. Okay, so we have zeros at 0, pi, and 2 pi, and so between 0 and pi, well, actually notice cos x minus 1, right? Cos x is less than or equal to 1. So cos x minus 1, this term here, is negative except at 0 and 2 pi, right? So this term is always negative except at the endpoints. and so we have to look at sine. So sine is positive in quadrants 1 and 2 from 0 to pi. It's negative from pi to 2 pi. And that means that, well, sine is positive from 0 to pi, but cos x minus 1 is negative. So overall, we have a minus sign there. We have a plus sign there. Okay? So now we know when the function is positive and when it's negative. Alright, so that's all the information we can get out of f. Now we want to look at f prime. So what's f prime of x? So for the first term, chain rule says we do, it's going to give me 2 cos 2x, right? So I do the derivative of sine, which gives me cos, evaluated at 2x, but then I got to multiply by the derivative of the 2x on the inside, which is where that extra factor of 2 comes from, minus 2, and then I have, derivative of sine gives me cosine. Alright, this time it takes a little bit more work to figure out the zeros. We want critical points, right? We want to know when f double prime is equal to 0. We want to know when it's positive, when it's negative. We want that sign diagram. So we need another identity. So we need the fact that cos 2x is 2 cos squared x minus 1. That's a trig identity. And with that identity, we get 4 cos squared x minus 2 cos x minus 2. Okay, so that's 2 cos squared x minus, 2 cos squared x minus cos x minus 1. And we say, okay, does that factor? Well, let's have a look. We can think of this as being quadratic in cosine, so if it's going to factor, it's going to have to look like this. 2 cos x with a 1, cos x with a 1, and if we put a minus sign there and we put a plus sign there, we can see that that is going to work out, right? 2 cos times cos gives me the 2 cos squared, minus 2 cos x plus 1, minus 2 plus 1 gives me the minus sign here, and then plus 1 times minus 1 gives me the minus 1. Okay, so that works out. And so what are my critical points? Well, I need either cos x equals, so if I take this term and I solve for cos, I move the 1 over, I set it equal to 0, move the 1 over, I get minus 1, divide by 2. So my critical points, I need cos x equal to minus 1/2. Now, between 0 and 2 pi, when is cos x equal to minus 1/2? That's going to be when x is equal to 2 pi over 3 or 4 pi over 3. Okay, in quadrants 2 and 3, that's where cosine is negative. Or again, we could have cos x equal to 1, and then we have again x equals 0 and 2 pi. So we got to keep that in mind as well. Those are actually critical points. Okay, so my sign diagram for f prime looks like this. Okay, 0, 2 pi, and I'm going to extend it a little bit, because I want to know 0 and 2 pi, right? Those are critical points. Once I kind of extend my domain to all real numbers, I want to know what's going on at those critical points. Are those minima? Are they maxima? What's happening at those points? So let's mark off the other two critical points. 2 pi over 3, 4 pi over 3. Okay, and once again, I know that cos x minus 1 is negative everywhere except at 0 and 2 pi, and so I've got to focus on the 2 cos x plus 1 and try to think about where is that positive and where is that negative. And so that takes a little bit more work. You could always try kind of plugging points in if you want. But basically, with a bit of work, you can find that between these two critical points, 2 cos x plus 1 is going to be negative, and everywhere else is going to be positive. And the easiest way to think of that, let me squeeze in a little unit circle here. Okay. Okay. There are the two angles where cos x is equal to minus 1/2, and if I'm in this region here, okay, cos x is in fact bigger than minus 1/2. In this region here, it's smaller than minus 1/2. And so whenever cos x is bigger than minus 1/2, this is going to be positive. Okay, so we know that this term is going to be kind of positive out here, and it's negative in there. Okay, so if you think about what that means, well, the 2 cos x plus 1, it's negative in this region here, but again, this part is negative, so we get a plus sign there. We get minus signs there, and we actually still get minus sign on either side of 0 and 2 pi, right? Because if you think about what's going on near 0, right? Cos x minus 1 is equal to 0 at 0 and pi, but as soon as you move away a little bit on either side, it becomes negative, and the other term, the 2 cos x plus 1, is positive there. So we get a sign diagram that looks like this. Okay, so then we can see from the sign diagram that we have horizontal tangents at 0 and 2 pi, so neither a minimum nor a maximum, and we go from decreasing to increasing, so this is a min at 2 pi over 3, and we go from increasing to decreasing at 4 pi over 3, so there we have a maximum. Okay, so the last thing to do is concavity. Before we do the sketch, we still have to do f double prime, right? So f double prime, okay, so here was f prime just for reference. F prime was 2 cos 2x minus 2 cos x. F double prime is going to be minus 4 sine 2x plus 2 sine x. Using the fact that the derivative of cos is minus sine, again we get an extra 2 coming from the chain rule in the first term. So again, we got to play around with trig identities here. This is minus 8 sine x cos x plus 2 sine x, and we can factor out 2 sine x, and we get 1 minus 4 cos x. Okay, so f double prime of x equals 0 when x equals 0 pi 2 pi, right, when the sine x term is 0, and also when cos x equals 1 over 4. Now that there's no kind of standard point on the unit circle that gives me cosine equal to 1 over 4, so there we just kind of have to, I guess the best we can do is we could say that on the unit circle, okay, here's a half, a quarter, so there's going to be an angle here. Oops. So one angle here, and this angle, say theta 1, and then we want cosine to be positive, right? So the other one is down here, and the other one is theta 2. So theta 1 is simply arc cos of a quarter. The other one, theta 2, well, remember that arc cos takes values in quadrant 1 and quadrant 2, so the inverse cosine function won't give me theta 2. The way to get theta 2 is to basically go all the way around by 2 pi and then realize that, well, theta 2, the related angle for theta 2 is theta 1, and one way to get it is like this, to go, that's 2 pi minus theta 1. So 2 pi minus our cos of 1 over 4. Okay, and that term, that 1 minus cosine of 1 minus 4 cos x, okay, so between those two angles, this is going to be where cos x is bigger than a quarter. Outside those two angles is where cos x is going to be less than a quarter, and when cos x is less than a quarter, this term is positive. Okay, and so when we work out the sign diagram for f double prime, 0, 2 pi, okay, there's also second derivative is 0 at pi, and we also have these points here, this theta 1 over here, theta 2 over here. Okay, so from 0 up to theta 1, this term is negative, sine is positive, so we have minus. From theta 1 all the way up to pi, the second term, the 1 minus cos 4x, that becomes positive. Sine is still positive up to pi, so this is positive. And then when we cross pi, well, then sine becomes negative, this remains positive. Okay, and so we get minus, we get plus. Okay, so that's what our concavity looks like. Alright, so now we are ready to attempt a sketch. So pi, 2 pi. Remember the other points that we needed here were we needed 2 pi over 3. We needed 4 pi over 3, which is over here. Okay, we need this theta 1, we need this theta 2. Okay, so there's an awful lot going on there. Now let's just jump back for a second. Let's look at, okay, zeros. What were the intercepts? Every multiple of pi is an intercept, right? So we know that we have zeros here, here, and here. Okay. We know that we have a local min at 2 pi over 3, a local max at 4 pi over 3. And we should actually plug those values in. Let me kind of squeeze that in up here. Okay. F of 2 pi over 3 is going to be sine of 4 pi over 3 minus 2 sine 2 pi over 3. Okay, which is minus root 3 over 2 minus 2 times root 3 over 2, which is going to be minus 3 root 3 over 2. And similarly, if we were to do sine of 4 pi over 3, or f of 4 pi over 3, we would get sine of 8 pi over 3 minus 2 sine 4 pi over 3. So where's 8 pi over 3? 8 pi over 3, well, 6 pi over 3 is 2 pi, so 8 pi over 3 is 2 pi over 3, 4 pi over 3, 6 pi, so we go 2, 4, 6, 8. So we're back in quadrant 2 where sine is positive, related angle is pi over 3, and so we get root 3 over 2 minus 2 times minus root 3 over 2. So then we get plus 3 root 3 over 2. Okay, the exact y values aren't super important, but let's plot those. Okay, so at 2 pi over 3, we've got a point somewhere down here. Right? it's negative. At 4 pi over 3, it's up here, it's positive. Okay? And let's keep in mind that our function is negative from 0 to pi, it's positive from 0 to 2 pi. And we're decreasing until we hit the min, then we increase up to the max, and then we decrease again. Okay, so last thing to notice is we've got a couple of inflection points. We've got one inflection point kind of right around here. The other inflection point is right around there. Okay, I think we're ready to connect the dots. Okay, so from 0 up to theta 1 we are decreasing and concave down. And remember we had a horizontal tangent at 0, so we go down like that. Inflection point at theta 1 we switch to concave up. We pass through the minimum. And we come up, we increase through pi. We become positive at pi. We head up through the maximum, back down. We become, concave down at theta 2. Okay. And we head down to 2 pi. Okay. And now, if we wanted to, we could repeat. So if we wanted to go from, say, up to 4 pi, well, now we kind of go down. We do the same thing over again. Okay, and if we wanted to go the other way, we can do that. And that graph just keeps repeating forever and ever in either direction. Okay, so that was a pretty tough one. If you can get through something like that, chances are you can handle just about anything that you might have to sketch.